Usually when we talk about a natural disaster or even just the impending threat of one, there is this overwhelming expectation of a singular primal
Right,
response.
you run, you get away.
Exactly. You get as far away as possible. Like if a Category 5 hurricane is barreling toward the coast, you don't stick around to see if you can harness the wind.
Yeah, no, you board up the windows, you pack your car, and you evacuate.
Self-preservation is entirely binary in those critical moments.
Mm.
You're either standing in the path of absolute destruction or you're safe.
It is a very human, very ancient instinct to look at the violent forces of the earth and simply retreat.
Right. But then you look at what is happening in Iceland right now, specifically on the Reykjanes Peninsula, and that binary response it shatters into a million pieces.
It really does. It's wild.
Because we are talking about a 15-kilometer-long river of molten magma running violently beneath the Earth's crust, slowly creeping toward the surface.
Yeah, and it's causing thousands of daily tremors.
Thousands. The entire coastal town of Grindavik had to be evacuated because the roads were literally being ripped apart by the sheer tectonic stress.
Yeah.
The ground is just expanding.
It's the absolute textbook definition of geological terror. You have this massive, highly volatile force of nature bubbling right under your feet.
Capable of erasing a town from the map in a matter of hours.
Right.
And yet, instead of just fleeing from this immense geological danger, sealing off the peninsula and abandoning the area entirely, the people of Iceland have done something that feels almost, I don't know, science fiction in its audacity.
They've effectively plugged into it.
They really have.
Mhm.
They figured out how to tap into the very same tectonic forces that are currently tearing their roads apart to power their civilization.
Which, requires a complete reframing of humanity's relationship with the Earth. What almost every other culture on the planet views as an apocalyptic threat, they view as an industrial engine.
Welcome to this deep dive. Today, we are taking you on an incredibly intricate journey into how Iceland has harnessed its highly volatile, downright dangerous geology to create a revolutionary, virtually zero-waste, renewable energy ecosystem.
And we have a massive, fascinating stack of source material guiding our conversation today.
Yeah, we're pulling from dense academic papers on geothermal agriculture and the deep earth chemistry of natural hydrogen. We have comprehensive technical reports on Iceland's geothermal infrastructure from 2020 to 2022.
We even have historical archives analyzing subarctic fruit production.
Which is crazy to me. Yes, we are actually going to spend time today talking about the logistics of Icelandic bananas.
It's a real thing, and our underlying mission for you today is to thoroughly explore a concept known in engineering circles as cascading energy utilization.
Cascading energy. I love that term.
Yeah, we're going to prove, using the Icelandic infrastructure as our master blueprint, that what we traditionally view as waste or industrial exhaust is actually a massively untapped, highly lucrative resource.
We are going to uncover some truly surprising realities along the way, too, like winter-blooming pansies surviving the snow in New York City and deep earth rocks that literally breathe out pure hydrogen fuel.
It's going to be a trip.
But to understand how any of this is possible, we have to start by looking at the engine itself, right? We have to look at the physical reality of where Iceland is sitting on the globe.
You simply cannot separate Iceland's energy innovation from its incredibly precarious geography. I mean, Iceland sits directly astride the mid-Atlantic ridge.
And for anyone who needs a quick refresher on plate tectonics, this is the massive planetary scale boundary between the North American tectonic plate and the Eurasian tectonic plate.
Exactly. And these plates aren't just sitting there in a static gridlock rubbing against each other like, say, the San Andreas Fault.
They're actively tearing apart, right?
They are. It's a divergent boundary. The convection currents deep within the Earth's mantle are physically pulling these two massive continental plates in opposite directions at a rate of about 2 centimeters a year.
Which, I mean, to put 2 centimeters a year into perspective, that is roughly the speed at which your fingernails grow.
It sounds incredibly slow.
It does. But over geological time, that is a tremendous, violent amount of movement. It's constantly ripping the Earth's crust open, creating massive fissures and fault lines.
Right. But Iceland possesses a second geological wildcard that makes it totally unique. It doesn't just sit on the ridge, it also sits directly on top of a massive mantle plume.
What geologists call a hotspot.
Yeah, hotspot.
So I want to visualize this properly. You have the Earth's crust, which is being pulled apart and stretched incredibly thin by the diverging plates. And right underneath that newly thinned out crust, you have a massive localized upwelling of abnormally hot, molten rock rising straight up from the deep mantle.
That is the exact mechanism. The simultaneous presence of the mid-ocean ridge pulling the crust apart and the hotspot pushing magma up has supercharged the magmatic activity in this region.
Basically since the Middle Miocene epoch, according to the sources.
Yeah.
Let's pause on the jargon for a second. The Middle Miocene epoch.
Right.
What kind of time frame are we talking about here, and why does that specific timeline matter to the energy grid today?
We're talking about roughly 15 million years ago.
Wow.
15 million.
Yeah, and it matters because it means this specific region of the Earth's crust hasn't just had a recent burst of volcanic activity. It has been subjected to a continuous, sustained, massive upwelling of thermal energy for millions of years.
So they haven't been on for a very long time.
Exactly. This prolonged combination creates the absolute perfect storm for high-temperature geothermal systems. I mean, to create a viable industrial-scale geothermal system, you essentially need three fundamental ingredients to occur in the same place at the same time.
Okay, let's break this down.
First, and most obviously, you need a massive heat source. In Iceland, because of that stretched, thinned crust and the underlying mantle plume, you have immense magma chambers sitting just a few kilometers below the surface. That part makes perfect sense. The fire is remarkably close to the floorboards. What's the second ingredient?
You need water. You need a colossal, constantly replenishing volume of water to capture that subterranean heat and physically move it to the surface where we can use it.
And Iceland definitely has water. It's a mountainous island sitting in the middle of the tempestuous North Atlantic Ocean.
It receives incredibly heavy precipitation. Plus, its higher elevations are capped by massive ancient glaciers.
So there's a constant, immense, seemingly infinite supply of what geologists call meteoric water rain, snowmelt, and glacial runoff just soaking into the ground every single day.
Right, so you have heat and water.
It sounds like the setup for a planetary-scale tea kettle. But the water has to actually reach the heat source, which means it has to get through miles of solid rock. That leads me to the third ingredient.
Yep. The third crucial ingredient is highly permeable rock. And this is where the specific geological history of Iceland becomes truly fascinating.
Tell me about the rock.
Well, Iceland's upper crust is predominantly made up of what geologists call Pleistocene basalts.
Okay, another geological era we need to unpack.
Right.
Pleistocene.
This refers to a period roughly between 2.5 million and about 11,700 years ago. It encompasses the recent series of major ice ages.
So lots of glaciers.
Massive, heavy ice sheets repeatedly covered Iceland. Now, volcanic eruptions would occur underneath these kilometers-thick glaciers.
That sounds violently dramatic.
Oh, it is. When 1,000-degree molten lava erupts directly into solid ice, it doesn't flow smoothly like you see in Hawaii. It cools almost instantaneously, undergoing immense thermal shock.
Yeah.
This rapid, violent cooling under extreme pressure shatters the rock as it forms. It creates vast formations of basalt that are incredibly brittle, highly fractured, and full of countless faults, cracks, and fissures.
It's like dropping a red-hot glass marble into a bowl of ice water. It just shatters internally.
A very apt comparison. Because of that shattered structure, combined with the ongoing tectonic tearing of the ridge we discussed earlier, the rock beneath Iceland acts less like a solid wall and more like a gigantic three-dimensional sponge.
It's a highly efficient plumbing system.
Exactly.
So how do these three ingredients, this shallow magma, the glacial water, and the shattered rock, actually interact to create the energy we extract?
They form what is called a hydroconvective system. The freezing cold surface water from the rain and glaciers seeps deep down into the earth through those microscopic fractures in the basalt.
Going down toward the magma.
Right. As it descends over several kilometers, it gets closer and closer to the magma chamber. Now, the water doesn't typically touch the liquid magma directly.
It doesn't. I always pictured it boiling directly on the lava.
No. Instead, it hits a relatively thin, solid layer of rock that acts as a highly conductive thermal boundary. The immense heat from the magma transfers through that rock layer into the descending water.
So it superheats.
It superheats, often well past its normal boiling point due to the extreme subterranean pressure. Because it's hotter, it becomes lighter and less dense than the cold water pushing down from above, so it rapidly, naturally convects, rushing back up through different fractures toward the surface.
Let me see if I have the mental model right. The entire island of Iceland is essentially a naturally occurring country-sized radiator system.
Basically, yes.
Tectonic forces have cracked the radiator open, the glaciers provide the coolant fluid, and the magma plume acts as the boiler. The Earth has built the entire industrial facility.
All humanity has to do is tap a pipe into it.
Right. But I want to push back on this narrative of Icelandic ingenuity for a moment. Because as you describe it, Iceland has won an incredibly unique, literally one in a million geological lottery.
They definitely have a geographic advantage.
They have the divergent ridge, the mantle plume, the subglacial shattered basalts, the glaciers. If their entire energy ecosystem is predicated on this hyper-specific geographical anomaly, does that mean everything we are talking about today is functionally impossible to replicate anywhere else?
That's a fair question.
Are we just studying a lucky fluke?
That is the essential, critical question to ask. If this only works in Reykjavik, it has no global value. But the answer to your question is a definitive no.
Okay, explain that.
We have to make a very clear distinction between the source of the thermal energy and the management of that energy. Yes, having a magma chamber a few kilometers down is a localized geological stroke of luck.
Sure.
But the engineering philosophy that Iceland uses to extract, distribute, and meticulously maximize every single drop of that thermal potential, that philosophy is universally applicable.
So you could apply it anywhere.
You can apply the Icelandic model of energy management to a nuclear plant in France, a solar array in Nevada, or a waste incineration facility in Japan. And that distinction bridges us perfectly to the core of their entire industrial philosophy, the concept of the cascade.
The cascade. I am deeply fascinated by this concept because it completely upends the industrial norms we've accepted for a century.
It really flips the script.
When we think of a traditional power plant, let's say a standard coal-fired plant or
Sure.
a modern combined cycle natural gas plant, the architectural and operational goal is entirely singular. You have one objective: make electricity.
Right, you burn a fuel, boil water, spin a turbine.
You generate your megawatts, and whatever immense thermal heat is left over after the turbine spins is just dumped, gets vented out of a massive concrete cooling tower directly into the atmosphere, or it's flushed into a nearby river. It is literally classified by engineers as waste heat.
The traditional industrial model is highly linear, remarkably short-sighted, and incredibly inefficient. You extract a primary resource, you pull one single value stream from it, and you discard the rest of the energetic potential into the environment.
But the cascade is different.
The Icelandic engineering community has fundamentally redefined that paradigm. When they look at a volume of superheated geothermal fluid coming out of the ground, they don't just see electricity, they see a multi-layered, multi-tiered resource.
Hence the term cascade system.
Exactly. In a cascade, the exhaust, the effluent, or the waste from one primary industrial process becomes the direct primary fuel source for the next process down the line.
Let's ground this abstract concept in reality. Let's look at the ultimate example of this cascading philosophy from our source materials. HS Urga's resource park at the Svartsengi geothermal power plant.
A fantastic example.
And this facility is located on the Reykjanes Peninsula, which, ironically, is the exact same area currently dealing with the tectonic tearing and the magma threat we discussed at the top of the show. When you look at the operational numbers on this plant, they are truly staggering.
They represent a masterclass in thermodynamic efficiency. To understand the cascade, you have to look at what they are pulling out of the earth at Svartsengi.
What exactly are they extracting?
The reservoir fluid that they extract via deep boreholes isn't just hot water. It is a highly complex, mineral-rich brine that is heated to 240 degrees Celsius.
240. Wow.
It is incredibly hot, highly corrosive, and under immense geological pressure.
So they bring this aggressive 240-degree brine rushing up to the surface. What is the very first step in the cascade? What is the top tier?
The first step is what you would expect from any standard power facility: electricity generation. They take the high-pressure steam that flashes off the brine as it reaches the lower pressure of the surface, and they run that steam through a series of conventional turbines.
Okay, pretty standard so far.
Right. The Svartsengi facility generates about 76.4 megawatts of electrical power, or MW, that provides clean baseload electricity for the regional grid.
But here is the critical juncture where the Icelandic model diverges from the rest of the industrialized world, right?
Exactly. Once that steam has physically pushed the heavy turbine blades and spun the generator, it has lost a significant amount of its pressure, but it retains a massive amount of thermal energy.
It is still incredibly hot.
Very hot. So instead of venting that lower pressure steam into the frigid subarctic air, they capture it. They pass that steam, along with the remaining hot brine, through a massive complex series of industrial heat exchangers.
I want to break down the mechanics of these heat exchangers. What exactly is happening inside them? Are they mixing the geothermal fluids with fresh water?
No, they cannot mix them. The geothermal brine drawn from deep within the earth is far too mineral-rich, saline, and highly corrosive to ever pump directly into municipal pipes or people's home radiators.
We would just eat through the pipes.
It would destroy the infrastructure in a matter of months. So they use a heat exchanger. Think of it as two separate networks of metal pipes running incredibly close to each other, often intertwined.
Okay, so they never physically touch.
Right. In one set of pipes, you have the dangerously hot, corrosive geothermal brine. In the other set of pipes, you pump pure, fresh, freezing cold groundwater drawn from shallow local aquifers.
And the heat just jumps across.
The physical heat from the brine conducts through the metal walls of the pipes and violently warms up the fresh groundwater. The fluids never touch, but the energy transfers perfectly.
It's brilliant.
And through this secondary process alone, Svartsengi produces a massive 190 megawatts of thermal energy in the form of hot, pure water.
And where does that 190 megawatts of thermal energy go?
It is pumped directly out to the surrounding municipalities. That secondary process provides the total space heating and hot tap water requirements for roughly 30,000 people living in the region.
So from one single extraction of geothermal brine, we have already secured baseload electricity for the grid, and we've entirely eliminated the need for 30,000 people to use gas or electric heaters in their homes.
That's two major, distinct revenue streams.
But according to the deep dive reports in our sources, HS Orca doesn't stop at two. This single extraction process at Svartsengi eventually cascades down into 8 or 9 entirely separate commercial revenue streams.
It is industrial efficiency elevated to a form of high art. If you track the utilization of that initial brine all the way down the cascade, the yields are phenomenal.
What else are they getting out of it?
From that one source, they're commercializing electricity, hot water for district heating, cold fresh water, industrial steam, geothermal mineral water, lava-filtered seawater, and they're even capturing and commercializing the carbon dioxide emissions that naturally bubble up with the brine.
I want to zero in on one of those streams because here's where the story gets really interesting and honestly a little bit funny. Let's talk about the geothermal mineral water stream.
Ah, yes.
Because this byproduct leads directly to one of the most famous, heavily photographed tourist destinations on the entire planet, the Blue Lagoon.
The famous Blue Lagoon.
I think the vast majority of people, myself included, before reading these sources, assume that the Blue Lagoon is this pristine, ancient, naturally occurring geothermal wonder. Can you imagine Vikings soaking in it after a long voyage?
Oh, absolutely. The marketing is great.
But our sources reveal a completely different, heavily industrialized, and almost accidental origin story.
It is arguably one of the greatest, most lucrative examples of a happy accident in modern industrial history. The story starts when the Svartsengi power plant first began its initial operations back in 1976.
Okay.
The engineers had successfully designed the electricity generation and the heat exchangers, but they ran into a massive, immediate logistical issue. After they extracted the thermal energy, they were left with a colossal volume of what is called effluent brine.
The leftovers.
Right. We are talking about discharging 42 liters of warm, mineral-heavy water every single second. They had to put it somewhere.
42 liters a second is a fire hose of industrial waste. You can't just put that in a tank.
You cannot. So the engineers looked at the surrounding landscape, which is comprised of vast, jagged lava fields. The standard geological assumption was that this specific type of igneous lava rock is highly porous.
It's full of air pockets and microfractures, right?
Exactly. It's highly permeable. The logic was simple. If we discharge the effluent brine directly onto the lava field, the water will simply percolate down through the porous rock and naturally return to the subterranean aquifers.
It seemed like the perfect low-cost disposal method.
And for the first few weeks, it worked exactly as designed. The water sank into the earth. But then the system encountered a critical chemical catch.
The silica.
The silica. Geothermal fluids in Iceland, particularly those drawn from deep, high-temperature reservoirs interacting with the salt, carry extremely high concentrations of dissolved minerals.
And the primary one is silica.
Yes, silicon dioxide. We're talking about massive concentrations, ranging between 0.6 and 1.2 grams of dissolved silica per liter of fluid. Now, when this brine is deep underground at 240 degrees Celsius and under immense pressure, The silica remains perfectly dissolved in the liquid.
Kind of like how sugar dissolves completely into hot tea.
That's a perfect analogy. But when the engineers dumped that effluent brine onto the cold surface of the lava field, the fluid rapidly cooled down and the atmospheric pressure dropped.
And as the temperature drops, the solubility of liquid drops. It can't hold the minerals anymore.
The physics dictated. The silica rapidly precipitated out of the solution. It didn't form hard crystals, though. Rather, it formed this thick, viscous, white colloidal mud.
Oh, wow.
This microscopic silica mud coated the jagged surface of the lava rock. More importantly, it seeped into the pores and microfractures of the stone and solidified.
Which effectively functioned as a microscopic grout, completely sealing the natural drain.
It hermetically sealed the lava field. It completely eliminated the permeability of the rock. So instead of sinking harmlessly back into the ground as the engineers intended, the 42 liters per second of effluent brine had nowhere to go.
It began to pool.
Over the months and years, it formed a massive, continuously expanding, milky blue artificial lake sitting right in the shadow of the power plant's cooling towers.
An industrial disposal problem on a massive scale. But then, according to the historical notes, the narrative shifts. People started sneaking in and bathing in this artificial waste lake.
They did.
Specifically, people suffering from the chronic autoimmune skin condition psoriasis discovered that bathing in this incredibly silica-rich, algae-filled wastewater actually had profound therapeutic effects.
It was clearing up their skin lesions in a way that modern medicine at the time couldn't replicate.
That is just wild. What began strictly as a colossal environmental disposal headache organically evolved into a medical revelation.
The management at HS Orca eventually realized the immense inherent value of this accident. They didn't just have a disposal pond, they had a therapeutic resource.
So they capitalize on it.
Big time. By 1999, they completely formalized and commercialized the operation. They engineered a specialized, man-made lagoon adjacent to the original spill site. They precisely controlled the inflow to maintain a steady, highly comfortable temperature of 37 to 39 degrees Celsius year-round.
And it's huge now, isn't it?
Oh, massive.
Uh-huh.
Today, the Blue Lagoon facility contains about 9 million liters of this specialized brine. The engineering ensures a hydraulic retention time of about 40 hours, meaning the entire 9 million liter volume of the lagoon is completely refreshed and replaced every 2 days, keeping it pristine.
That's incredible. And it's salty, right? But not like the ocean.
Right. The specific mineral composition settles at a salt content of about 2.5%, which is roughly 70% the salinity of standard seawater. That makes it uniquely buoyant and gentle on the skin.
The scale of the pivot is astonishing. We're talking about a site that currently hosts almost 1 million international tourists every single year.
They operate an internationally recognized, specialized clinical facility dedicated entirely to treating psoriasis patients right there.
And they manufacture and export a highly lucrative line of expensive, premium skincare products utilizing the silica mud, the minerals, and the unique microalgae that thrives in that specific water temperature.
And the entire operation, this massive driver of the Icelandic tourism economy, is fueled entirely by the exhaust pipe of the power plant next door.
And the cascading innovation regarding this specific mineral doesn't even stop at tourism, does it? That same silica scaling that accidentally created the lagoon. I mean, ask any geothermal engineer anywhere in the world about silica scaling, and they will tell you it is their worst nightmare.
Oh, it's a massive headache. It builds up inside the expensive metal extraction pipes, restricting flow and eventually ruining the infrastructure, requiring massive maintenance budgets to clear.
But a specialized spin-off company called Geosilica looked at that exact same scaling issue and saw yet another unmonetized solution.
They really did. They spent years developing a proprietary process to cleanly harvest that silica directly from the geothermal fluid before it could damage the pipes.
And then what do they do with it?
They refine that harvested silica and turn it into 100% natural, premium liquid dietary supplements and topical skincare products.
They literally took the most expensive maintenance headache in the plant and turn it into a high-margin retail product.
Yeah.
It is a brilliant pivot.
Truly brilliant.
You take the electricity to power the grid, you take the thermal heat to warm the town, you take the cooled water to build a world-class spa, you take the algae for cosmetics, and you take the pipe-clogging minerals for dietary supplements. Nothing is allowed to be wasted.
When you zoom out and look at the macro-level industrial architecture, this is the fundamental paradigm shift that the rest of the industrialized world needs to internalize. In the Icelandic engineering mindset, the concept of waste does not exist in a permanent state.
Waste is just an asset without a mark yet.
Exactly. Waste is simply a valuable raw material that hasn't yet been introduced to its correct market.
I want to transition from the high-end retail applications, the spas and the supplements, back to the heavy foundational infrastructure. We've established that the cascade provides electricity. But where is the sheer, overwhelming bulk of this massive thermal energy actually going on a daily basis? Let's take a really deep dive into how Iceland approaches the concept of heating.
Heating is where geothermal energy moves from an abstract industrial concept to something that physically shapes the intimate daily life of every single Icelander. The macro statistics are critical to understand here.
Give us the numbers.
Geothermal energy provides a staggering 65% of Iceland's total primary energy supply across all sectors. But when you drill down into the direct use of that geothermal energy, which categorizes all the thermal energy utilized for purposes other than spinning a turbine to generate electricity, 72.8% of that total volume goes to one single application.
Space heating.
Space heating. Over 90% of all residential homes, commercial buildings, and public facilities in Iceland are heated entirely by geothermal district networks.
I need to pause and emphasize that statistic for you, our listener. Over 9 out of 10 homes in an entire nation are heated by piping hot water straight out of the ground. That is a wild, almost incomprehensible infrastructure reality for someone living in North America or most of Europe.
It really is.
And reading the historical sources, this isn't a recent high-tech green initiative, is it? It started over a century ago. The texts mention a local farmer back in 1908 in a place called Suðuroyar.
Yeah, he didn't wait for a municipal grid. He basically jury-rigged a 500-meter pipeline out of whatever materials he had, running it from a boiling hot spring directly into the radiator of his farmhouse.
He was the undisputed pioneer of the concept. He proved the fundamental viability of direct application.
And from that single farmhouse, the concept began to scale, albeit slowly at first. By 1930, the municipality laid a rudimentary 3-kilometer hot water pipeline from the Laugardalur hot springs straight into a hospital and a few schools in Reykjavik.
But the true aggressive catalyst for the massive infrastructure we see today wasn't environmentalism, was it? It was brutal economic reality.
The global oil crisis of the 1970s.
Precisely. In the 1970s, geopolitical tensions caused the price of imported fossil fuels to skyrocket almost overnight.
For an isolated island nation entirely dependent on importing coal and oil to survive the brutal subarctic winters, this was an existential economic threat. It crippled their balance of trade.
So what did they do?
In response, the Icelandic government made a highly aggressive, deeply strategic, nationalized push to permanently decouple their heating infrastructure from the volatile global oil market. They poured massive capital into expanding the domestic geothermal district heating grids.
And to give you a sense of the transition, in 1970, approximately 43% of all homes in Iceland were heated by burning imported oil. Today, that number is functionally zero.
The speed of that transition is incredible.
But I want to dig into the actual physical logistics of this system today, because the scale of an operation like Reykjavik Energy is mind-boggling. We're talking about a farmer tapping a hot spring in his backyard with a 500-meter pipe anymore. They are moving literal oceans of boiling water across vast, unforgiving terrain.
The modern engineering required to achieve this is phenomenal. Let's examine the Nesjavellir power plant as our primary example. It is a massive, high-temperature extraction field located in the Hengel volcanic area, which is situated roughly 27 kilometers away from the city of Reykjavik.
Okay, 27 kilometers.
They drill deep into the reservoir and bring up a volatile, two-phase mixture of high-pressure steam and geothermal liquid. This fluid reaches the surface at an astonishing 192 degrees Celsius.
Just to do the quick conversion for our listeners, 192 degrees Celsius is nearly 380 degrees Fahrenheit. It is wildly, dangerously hot.
Very hot.
And the sources note it comes up under a pressure of 12 barg. I know we skipped over this earlier, but what does barg actually mean in practical terms?
Right, so bargarg stands for bar gauge. It is a unit of pressure relative to the ambient atmospheric pressure. 1 bar is roughly equivalent to the normal atmospheric pressure at sea level. So 12 barg means the fluid is under 12 times the pressure of the normal atmosphere.
That's intense.
This immense pressure is critical. It is the only physical force preventing that 192-degree water from instantly flashing entirely into steam as it races up the borehole.
Okay, so you have this incredibly pressurized, superheated brine at the surface. As we discussed with Svartsengi, this specific fluid is highly corrosive. You cannot pipe it 27 kilometers into the city.
You cannot. So at the Nejvelair facility, they utilize massive centrifugal separators to divide the steam from the liquid water. The dry steam is routed to the turbines to generate electricity for the national grid.
And what happens to the remaining thermal energy?
The heat from both the spent steam and the separated hot brine is directed into colossal titanium plate heat exchangers. Just like at Svartsengi, they use this thermal energy to flash heat pure, cold, fresh groundwater drawn from a nearby lake.
But the sources detail a very specific, highly technical step they take next to protect the infrastructure. After they use the heat exchangers to warm up the fresh groundwater, they deliberately inject a tiny, highly calibrated amount of geothermal steam, specifically steam containing hydrogen sulfide gas, back into the newly heated fresh water.
Yes.
I have to admit, when I read that, it sounded completely counterintuitive. Why would you go through all the trouble of separating the toxic, corrosive geothermal gases only to intentionally inject a toxic gas like hydrogen sulfide back into the pure drinking water you are about to pump to the city?
It sounds counterintuitive until you understand the deep chemistry of pipeline corrosion.
Let's hear it.
When you heat up fresh, aerated groundwater, the dissolved oxygen within that water becomes incredibly reactive. If you pump highly oxygenated 80 degrees Celsius water through 27 kilometers of massive carbon steel pipelines, that dissolved oxygen will violently attack the iron in the steel.
It'll just rust it out.
It will cause rapid oxidation, severe pitting, and catastrophic scaling. The pipeline would rust from the inside out in a matter of months. They inject the hydrogen sulfide gas because it acts as a highly efficient chemical scavenger.
A scavenger.
Yeah, the hydrogen sulfide molecules actively seek out and bind with any remaining dissolved oxygen molecules in the fresh water.
Oh, wow. So they're basically setting up a chemical reaction inside the water that consumes the oxygen before the oxygen has a chance to consume the steel pipe.
That is the exact mechanism. By chemically scrubbing the oxygen out of the fluid using a trace amount of native gas, they completely eliminate the primary driver of corrosion.
That's brilliant.
This singular chemical intervention extends the operational lifespan of those massive steel pipelines by decades, saving billions of krona in replacement costs.
That is a profoundly elegant piece of chemical engineering. It uses the problem to solve the problem.
Exactly.
So now they have this chemically stabilized, superheated fresh water sitting at the Isravler plant. But the plant is 27 kilometers away from the city radiators. Do they use massive industrial pumps to force millions of gallons of water across that distance?
They rely on a far more reliable zero-emission energy source, gravity.
Gravity.
The Nejvelair plant is strategically located at an elevation of roughly 160 meters above sea level. They do use pumps initially, but only to push the heated water up a relatively short incline to a massive surge tank positioned at an elevation of 400 meters on a nearby ridge.
And from there?
Once the water reaches that 400-meter peak, gravity takes over entirely. The water simply flows downhill, continuously accelerating through massive, heavily insulated 1-meter diameter pipes, traveling the remaining 27 kilometers down into massive storage tanks situated on the outskirts of Reykjavik.
That insulation must be incredible.
It is so effective that the water only loses about 1 to 2 degrees Celsius during the entire journey. From the storage tanks, it flows effortlessly into the city's intricate, highly branched distribution grid. The efficiency is staggering. They are passively moving approximately 1,640 liters of 83 degrees Celsius water into the city every single second, 24 hours a day.
And this journey of the water brings us to one of my absolute favorite, deeply pragmatic details from the source reports. The cascade doesn't end when the water hits the radiator.
No, it doesn't.
We've moved the water 27 kilometers. It has entered a residential home in downtown Reykjavik. It has cycled through the metal radiators in the living room, transferring its heat into the air to keep the family warm during a blizzard.
Right.
The water has now cooled down significantly, but it is not freezing cold. It exits the house sitting at roughly 35 degrees Celsius, which is about 95 degrees Fahrenheit. It is essentially the temperature of a warm bath.
Exactly.
In almost any other city on Earth, a homeowner or a factory would just dump that 35-degree water straight into the municipal sewer system. But in Iceland, that water goes directly under the public sidewalks.
Snow melting infrastructure. It is perhaps the most visible, tangible daily application of the cascading energy principle for the average citizen.
It's so cool. Tell us how it works.
The municipal engineers take that spent 35-degree return water from the residential and commercial buildings, and before it goes to the sewer or out to sea, they route it through extensive networks of durable plastic cross-linked polyethylene tubing buried just beneath the concrete sidewalks, the public squares, and the asphalt parking lots.
And it actually melts the snow.
Completely. The capital area alone currently boasts over 1.2 million square meters of pavement heated by this specific cascade method. In downtown Reykjavik, during the darkest, most brutal subarctic winter storms, virtually every major pedestrian walkway remains completely free of snow and black ice.
Now, I have to be completely honest here. When I first read about the snow melting systems, my immediate cynical thought was, okay, running complex plumbing under your driveway just so you don't have to put on boots and shovel snow. That sounds like the absolute pinnacle of decadent luxury. It sounds like something only a wildly wealthy, energy-blind nation would do. It felt frivolous compared to generating electricity.
It absolutely sounds like a profound luxury right up until you dig into the hard economics and the energy expenditure metrics. Let's contextualize this by comparing the Icelandic system to how engineered snow melting is approached in the United States.
Let's do it.
According to the rigorous engineering standards published by the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or AHRAE, the standard thermal energy requirement to keep a commercial sidewalk free of snow accumulation in a climate like New York City or Chicago requires blasting roughly 222 BTUs of heat energy per square foot.
Okay. And in America, that energy is almost always generated by burning dedicated natural gas in a boiler, specifically for the driveway.
Exactly.
So 222 BTUs per square foot for New York. What is the comparative metric in Iceland?
Because the Icelandic systems are uniquely designed to operate continuously, using low-grade, high-volume, 35-degree waste heat that has already served its primary economic purpose, their systems run efficiently on just 55 BTUs per square foot.
55.
They are achieving the exact same, completely snow-free result while utilizing precisely 1/4 of the thermal energy required by the American standard.
Wow. They get the same result with 75% less energy.
Precisely. And more importantly, you have to look at the macroeconomic impact on the municipal budget. This isn't just about saving energy. It is a massive economic driver.
How so?
By utilizing the tail end of the geothermal cascade to passively melt the snow, rather than deploying fleets of diesel-burning snowplows, spreading thousands of tons of corrosive road salt, and treating slip-and-fall injuries in the hospitals, the city saves an absolute fortune.
Plus, the roads must last longer.
Exactly. By keeping the asphalt at a constant, stable temperature, they completely eliminate the destructive freeze-thaw cycle that creates potholes, meaning the roads last exponentially longer. Economic models estimate that the snow melting system actually saves the Icelandic economy roughly $68 million US, or about 9.5 billion Icelandic krona, every single year.
It's unbelievable.
It is the exact opposite of a decadent luxury.
Yeah.
It is a hyper-efficient, highly lucrative infrastructure investment.
It completely flips the script. You aren't paying to heat the sidewalk. The heated sidewalk is paying you back by protecting the asphalt and the pedestrians.
Exactly.
So the geothermal cascade gives us baseload electricity, world-class medical spas, cheap home heating, and dry, safe sidewalks in the middle of a blizzard. Now, I want to execute a hard pivot to a topic that sounds like it belongs on a late-night internet conspiracy forum.
Oh, I know where this is going.
When we were researching for this deep dive, I kept remembering this bizarre claim I've seen floating around message boards for years. The claim is that Iceland, this rugged, isolated subarctic island of jagged glaciers and erupting volcanoes, is actually Europe's largest producer of bananas.
It is arguably one of the most persistent, perfectly structured internet myths in existence, primarily because it combines two wildly incongruous, highly memorable images, a tropical fruit and a subarctic glacier.
Right. So is it true?
I need to be clear right off the bat. The core claim that they are the largest producer is demonstrably entirely false. If you look at the actual trade data from the UN's Food and Agriculture Organization, France, by virtue of its overseas territories like Martinique and Guadeloupe and Spain via the Canary Islands, are the undisputed largest producers of bananas in Europe. However, what makes the myth so resilient is that the foundational premise hides an astonishing, highly documented historical truth. Iceland absolutely does grow bananas.
Wait, they actually grow a tropical fruit on a commercial scale.
They do. And more importantly, for a period of time, they did it on a fully commercial scale intended for the domestic market.
I am struggling with the biology of this. How is that physically possible? A banana plant evolved at the equator. How does it survive a few degrees south of the Arctic Circle?
The mechanism to make it survive all comes back to harnessing the geothermal engine we've been discussing. To understand the logic, you have to look at the unique macroeconomic situation Iceland found itself in during the years immediately following World War II.
What was going on?
During the late 1940s, Iceland had aggressively begun to harness very inexpensive, highly abundant geothermal power on a massive scale for district heating. However, they faced a severe problem regarding food diversity.
They couldn't get fresh fruit?
Because of incredibly high import tariffs, severe post-war shipping restrictions, and the sheer cost of refrigerated transport over the ocean, the retail prices for importing fresh fruit from tropical climates were astronomically prohibitively high for the average citizen.
So an enterprising agricultural engineer looked at a boiling hot spring, looked at the price of an imported apple, and thought, with unlimited free heat, I can just build a jungle indoors.
That was essentially the exact business plan. Between 1945 and roughly 1959, various agricultural entrepreneurs constructed a significant number of specialized, massive glass greenhouses specifically dedicated to the commercial production of bananas.
That's wild.
By utilizing the free, limitless geothermal hot water, they could easily maintain the perfect, sweltering 30 degrees Celsius ambient temperature inside the greenhouse completely, regardless of the howling blizzards and freezing temperatures occurring inches away on the other side of the glass.
So they solved the temperature problem completely. But obviously, we aren't all buying product of Iceland bananas at our local grocery stores today.
Right.
What killed the industry? If the heat was basically free, why did commercial production collapse in 1959?
The fatal flaw in their business model wasn't the thermal heat, it was the biology of photosynthesis. Bananas are fundamentally equatorial plants.
They need a lot of sun.
Exactly. Their genetic structure evolved over millions of years to absorb intense, direct, overhead sunlight for roughly 12 consistent hours a day, 365 days a year. In Iceland, the solar reality is drastically different.
Yeah, the winters are super dark.
During the depths of winter, the sun barely crests the horizon for a few meager hours a day, providing very weak, highly angled light. Because of the extremely low annual sunlight levels, an Icelandic banana plant cannot photosynthesize fast enough to grow at a normal rate.
So how long does it take?
Consequently, an Icelandic banana takes roughly 2 entire years to mature and bear fruit.
2 years? That's absurd. Compared to, what, a few months of growth at a plantation on the equator?
Exactly. The geothermal heat could brilliantly simulate the ambient temperature of a tropical jungle, but the engineers at the time had no way to simulate the intensity and duration of the equatorial sun.
So it just took too long.
The 2-year growth cycle meant the land and the capital were tied up for far too long to be truly, sustainably profitable. The final, fatal blow to the industry came in 1960.
What happened in 1960?
The Icelandic government fundamentally altered its trade policy and completely removed the heavy import duties on foreign fruit. Almost overnight, inexpensive, fast-growing bananas shipped in from vast plantations in South America flooded the domestic grocery stores. The domestically grown 2-year bananas simply couldn't compete on price or volume, and commercial production ceased entirely.
But according to the deep dive reports, the plants themselves didn't entirely disappear. The sources indicate there are actual survivors of this experiment still alive today.
There is a thriving living museum dedicated to this agricultural experiment. When the commercial farms realized they couldn't compete and began shutting down their operations rather than destroying the crops, they donated their mature banana plants to what was then the National Horticultural College.
And they kept them alive.
Today, that institution is the Agricultural University of Iceland. They maintain the last remaining active banana farm in the country inside one of its specialized tropical greenhouses. They carefully tend to a permanent rotating grove of about 600 to 700 banana plants.
That is an amazing visual. 600 towering banana trees growing in the subarctic snow. Do they actually still produce edible fruit, or are they just ornamental at this point?
They absolutely produce viable fruit. The University Grove yields roughly 100 heavy clusters of bananas every single year, with each cluster weighing anywhere between 5 and 20 kilograms.
But they don't sell them.
No, they aren't sold in supermarkets. The entire annual harvest is consumed internally by the students, the researchers, and the staff of the university.
I have to say, sitting in a cafeteria while a blizzard rages outside, Eating a banana that took 2 brutal years to grow in a geothermally heated subarctic greenhouse sounds like a profound, uniquely Icelandic culinary experience.
It really does.
But while the banana experiment was ultimately a commercial dead end, the concept of greenhouse agriculture in general is a massive, highly successful pillar of the Icelandic economy today, isn't it?
Oh, absolutely. It is a foundational element of their national food security. Today, they operate approximately 200,000 square meters of highly advanced commercial greenhouse space.
And I'm guessing they figured out the sunlight problem.
They have completely solved the sunlight problem that killed the bananas. By utilizing their incredibly cheap, 100% renewable geothermal and hydroelectric electricity, modern farmers power massive arrays of intense, computer-controlled artificial LED grow lights.
To simulate the sun.
These specialized lights perfectly simulate the specific light spectrums needed for photosynthesis, supplementing the weak winter sun. As a result, these high-tech, glowing greenhouses currently cultivate and supply roughly half of all the fresh tomatoes consumed in the entire country and almost 100% of the fresh cucumbers.
Which is an incredible triumph of engineering over geography, ensuring fresh food security on an isolated volcanic rock. But here is where our deep dive takes a sharp turn from historical anecdotes into the absolute bleeding edge of modern agricultural science.
This is my favorite part.
We know you can build a glass box and heat the air inside it. But what if you didn't need the glass at all? What if you didn't need the expensive, fragile greenhouse walls? What if you could just directly hack the thermodynamics of the soil itself?
This specific inquiry brings us to a truly fascinating, rigorous academic study outlined extensively in our source materials. It was a joint cross-border scientific venture conducted between researchers at the Cooper Union in New York and agricultural scientists at the University of Iceland.
Okay, what were they doing?
They were rigorously testing a highly experimental concept they define as energy-intensive, shallow, geothermal, heated ground agriculture.
Let's break that dense academic title down.
Right.
What does the physical architecture of shallow heated ground agriculture actually look like in practice?
Imagine the precise engineering of the snow melting system we discussed earlier for the city sidewalks. But instead of laying those plastic pipes underneath a layer of impenetrable asphalt or concrete, you lay them directly underneath a bed of fertile, organic topsoil.
Oh.
At the Agricultural University campus, the researchers built a highly controlled experimental garden. They excavated a patch of earth and meticulously laid down a dense, mathematically spaced network of 2.5 centimeter diameter polypropylene plastic pipes. They placed these pipes incredibly close to the surface, burying them just 10 to 20 centimeters deep in the soil.
10 to 20 centimeters. I want to make sure I'm picturing this correctly. That is incredibly shallow. That is practically right at the root line of a standard vegetable plant.
That is the specific intent. The pipes were laid out in a highly dense, continuous spiral configuration, with the parallel lines spaced just 25 centimeters apart from each other, resting on a stabilizing bed of compacted, insulating sand.
Got it.
Once the grid was buried into the topsoil, they began circulating a continuously heated fluid through this closed-loop network. To get the heat, they tapped directly into a nearby high-temperature geothermal borehole that was steadily supplying high-pressure steam at roughly 100 to 125 degrees Celsius.
So they use that steam to heat the fluid in the pipes.
Exactly. They routed that raw, volatile steam through a traditional industrial shell and tube heat exchanger. The steam transferred its massive thermal payload into a separate, closed-loop working fluid that circulated through the buried plastic pipes.
And the source documents are incredibly specific regarding the chemistry of this working fluid. It wasn't just pure water cycling through the soil pipes. The researchers utilized a precise mixture of water and 20% automotive antifreeze.
They did.
Why introduce a toxic chemical like antifreeze into an agricultural experiment?
It was a vital, non-negotiable engineering safeguard necessary to prevent catastrophic system failure. If the central circulation pump were to fail, or if the geothermal steam supply experienced an unexpected interruption during the absolute depths of an Icelandic winter, pure water sitting stagnant in those shallow pipes would rapidly freeze, expand, and violently burst the entire plastic network, destroying the experiment.
Oh, of course. The antifreeze stops the pipes from bursting if the system goes down.
The 20% glycol mixture lowered the freezing point of the fluid enough to survive a total shutdown. Once the fluid was protected, a sophisticated, self-acting Danfoss temperature controller was installed.
To regulate the heat.
This automated valve mechanically regulated the flow rate, ensuring the circulating fluid maintained a constant temperature of 40 degrees Celsius during the mild summer months, and ramping up to a blistering 65 degrees Celsius during the colder, freezing months.
So you have a grid of plastic pipes sitting just a few inches below the dirt, continuously pulsing with 65-degree fluid. What did that massive injection of thermal energy actually do to the physical properties of the soil itself?
It fundamentally and aggressively altered the microclimate of the Earth. Extensive sensor data showed that the baseline soil temperature, measured at a consistent 10-centimeter depth directly above the pipes, was permanently elevated to sit between a balmy 25 and 40 degrees Celsius, regardless of the ambient air temperature above ground.
That's correct.
They had successfully engineered a localized patch of tropical equatorial Earth sitting directly in the middle of a freezing subarctic field.
And then the researchers took the ultimate leap of faith. They planted tomatoes, not inside a glass greenhouse, but right out in the open air, exposed to the Icelandic wind.
Exactly. To ensure scientific validity, they ran a highly strict side-by-side control test. They constructed a 5 by 10 meter geothermally heated garden bed, and directly adjacent to it, they built a 5 by 5 meter unheated control garden bed. Both beds were constructed utilizing the exact same soil composition, the same fertilizer, and the same ambient weather exposure.
And then they planted them.
On July 1st, they transplanted identical vulnerable tomato seedlings, specifically utilizing robust commercial varieties like 4th of July, Best Boy, and Steak Sandwich into both beds.
And I think it's safe to assume that the plants sitting in the control garden, the ones trying to grow in the freezing, unheated dirt, did not fare particularly well.
The control plants suffered immensely. The unheated tomatoes experienced such severe thermal stress that their physical mass actually shrank over the observation period by about 13%.
Shrinking tomatoes.
Yeah. Furthermore, a parallel batch of unheated cucumbers they planted alongside the tomatoes perished entirely from the cold. But the results recorded in the heated beds, the data was absolutely explosive.
I love data. Walk me through the exact numbers of the yield difference.
The tomato plants rooted in the geothermally heated outdoor soil didn't just survive, they thrived. They successfully endured several heavy early-season frosts that, by all biological metrics, should have instantly ruptured their cellular walls and killed them.
But they survived.
When compared directly to the struggling unheated control group, the heated tomato plants grew a massive 32% taller. They produced a truly staggering 176% more individual viable tomatoes, which resulted in an overall yield of 63% more total fresh harvest weight.
Producing 176% more tomatoes entirely outdoors in Iceland, simply by pumping waste heat into the dirt. That is remarkable.
It's a game changer.
But there is a specific biological detail recorded from the autopsy of the study that I find absolutely fascinating. When the researchers finally dug up the plants at the end of the short growing season to examine the root structures, they found something unexpected.
Thermotropism.
The root systems of the tomatoes in the unheated control beds looked perfectly normal. They had grown straight down and spread out evenly, searching for nutrients. But the root systems of the tomatoes in the heated beds had physically, dramatically altered their biological growth patterns.
It's amazing to look at the photos.
The roots hadn't grown down. They had grown horizontally, and they had physically tightly wrapped themselves entirely around the hot water pipes.
It is a stunning visual example of thermotropism. The plants were not passively existing in the warmth. Their biology recognized the heat source, and the roots actively sought out and physically embraced the 65-degree pipes to maximize their thermal absorption.
It's the biological equivalent of heated car seats for tomatoes. They just huddled around the warmth like a campfire.
That's a great way to put it.
But as fascinating as a subarctic outdoor tomato is, the natural skepticism kicks in. Does this have any application outside of Iceland? If I'm an urban planner or a farmer in a different country, why do I care about this specific experiment?
Well, the Cooper Union researchers clearly anticipated that exact question.
Because they took this Icelandic model and immediately ran a parallel experiment in the middle of a concrete jungle, New York City.
They did. They recognized that the core innovation wasn't the geothermal water itself, it was the utilization of low-grade waste heat. And while New York City certainly doesn't have bubbling magma plumes or geothermal hot springs, it produces a staggering, almost incomprehensible volume of industrial waste heat every single day.
Where does that heat come from?
The researchers decided to tap into the waste steam condensate generated by the massive consolidated Edison Municipal District heating system. This is the vast network of underground steam pipes that heats thousands of skyscrapers across Manhattan. Normally, after the steam has circulated through a building and heated the offices, it cools down and condenses back into hot water.
And what do they usually do with it?
By municipal law, this hot waste steam condensate must be aggressively cooled down using massive volumes of potable, clean city drinking water before it can be legally flushed into the municipal sewer system in order to protect the sewer pipes from thermal damage.
Which, if you think about it, is a catastrophic double waste. You are throwing away massive amounts of highly valuable thermal energy, and you are wasting thousands of gallons of perfectly clean drinking water just to cool down the garbage energy so you can throw it away safely.
It is the ultimate linear inefficiency. So the researchers at the Cooper Union proposed an elegant intervention. They intercepted that waste steam condensate. Instead of cooling it with drinking water, they routed that hot fluid into an identical network of plastic pipes installed within the shallow soil of elevated green roofs situated on top of buildings in the city.
And to truly test the limits of the extended season, instead of summer tomatoes, they planted delicate pansies.
Planting fragile pansies on a wind-whipped roof in December.
That sounds like a setup for failure. They transplanted the delicate flowers on December 23rd, right into the teeth of the incoming winter.
And the recorded results were just as dramatic, if not more so, than the Icelandic tomato experiment. The pansies, rooted in the heated green roofs, didn't just survive the freezing temperatures and the snow. They actively bloomed right through the darkest, coldest months of the New York winter.
Just blooming in the snow.
The researchers noted in the report that the flowers bloomed with the vigor and color as if they were in Florida. When measured against the unheated control roofs, the heated pansies grew 24% taller, achieved a 33% wider physical spread across the soil, and, most importantly, produced 45% more viable flowers and buds.
So if I synthesize the data from both experiments, what does this actually mean for the listener? Why should an urban planner in Chicago or a farmer in Germany care about buried hot water pipes?
They should care because this data completely shatters humanity's traditional, deeply ingrained understanding of rigid regional agricultural growing seasons. By intelligently capturing and utilizing low-grade waste heat, whether that heat comes from a bubbling geothermal exhaust pipe in a remote Icelandic lava field, or from the steam condensate returning from the basement of a skyscraper in Manhattan, you possess the physical ability to artificially extend the outdoor agricultural growing season by a minimum of 4 solid weeks.
Which is huge for farmers.
Furthermore, you can dramatically increase the overall crop yields of that land, completely without the massive capital expenditure of building, maintaining, and powering expensive glass or plastic greenhouses. It represents a massive, highly scalable leap forward for the viability of urban farming, local food resilience, and global food security in colder climates.
It effectively changes the map of where and when we can sustainably grow our food. It blurs the lines of the climate zone.
It definitely does.
Okay, we have talked at length about agriculture, tomatoes, and pansies.
Yeah.
But I want to take this core concept of the cascade, this idea of using waste heat to fuel a secondary process, and examine how it applies to heavy commercial industry. Because if you have enough captured energy to manipulate the thermodynamics of acres of soil, you have enough energy to manipulate much heavier, far more energy-intensive biological processes. Let's look at the actual coastline. Let's explore the concept of industrial symbiosis. I genuinely love this term. Symbiosis. In biology, it describes different organisms living off each other in a mutually beneficial loop. Here, we are talking about different, entirely unrelated, massive corporations living off each other's exhaust.
Symbiosis is the absolute perfect word to describe the architecture here. In a healthy, balanced natural ecosystem, like a deep forest, the concept of waste is biologically non-existent. The fallen leaf of one tree becomes the vital nutrient for the fungi, which becomes the food for the insect, which feeds the bird.
The waste of one organism is the essential fuel for another.
Exactly. Iceland has deliberately, meticulously engineered its modern industrial zones to physically mimic the nutrient loops of a forest floor. Let's examine the operations at the Stolt Sea Farm, which is a massive aquaculture facility located on the rugged Rick Johns Peninsula.
Okay, an industrial-scale fish farm on the coast. What specific species of fish are they cultivating?
They are cultivating Senegalese sole. It is a highly prized, highly lucrative gourmet flatfish, heavily demanded by high-end restaurants across Europe.
I need to stop you there. Senegalese sole, as in a fish native to the warm coastal waters of Senegal in West Africa, being commercially farmed on an isolated, freezing rock sitting just a few degrees south of the Arctic Circle.
It sounds impossible, right?
The water temperature difference alone makes that sound impossible.
The biology is extremely demanding. Senegalese sole are incredibly sensitive to temperature fluctuations. To thrive, grow at a commercial rate, and remain disease-free, they require a constant, unwavering water temperature of exactly 21 degrees Celsius.
And the ocean in Iceland is definitely not 21 degrees.
The natural ocean water crashing against the shores of Iceland is freezing. It hovers around 5 to 10 degrees Celsius, which would kill the sole instantly. But the Stolt Sea Farm isn't relying on the ocean's temperature. They strategically built their sprawling aquaculture facility directly adjacent to HS Orca's 100-megawatt Reykjanes geothermal power plant.
So the power plant next door is acting as the massive central heater for the fish tanks.
Yes, but the specific engineering of how they acquire that heat is where the genius of the cascade lies. The Reykjanes power plant utilizes a massive volume of cold seawater to constantly cool down its massive tubular steam condensers.
Okay, so the seawater is absorbing the waste heat.
As this cold seawater flows through the plant and absorbs the immense waste heat radiating off the spinning turbines, it undergoes a massive thermal shift. When that seawater finally exits the power plant's discharge pipe, it has been heated from ocean temperatures up to a remarkably consistent 35 degrees Celsius.
But wait, 35 degrees Celsius is practically bathwater. That is far too hot for the fish. If they need 21 degrees, 35 degrees will cook them.
Precisely. So the engineers at the fish farm execute a brilliant, low-energy thermodynamic balancing act. They intake that free 35-degree waste seawater pouring out of the power plant's exhaust. Then, they simply mix it with freezing cold, highly oxygenated fresh seawater that they pump from shallow, localized coastal wells.
Oh, that's clever.
By continuously mechanically adjusting the mixing ratio of the hot exhaust water and the cold well water, they can perfectly dial in and maintain a continuous, flawlessly stable flow of 21 degrees Celsius water through their massive rearing tanks.
That is brilliant. They don't spend a single krona burning fuel or using electricity to actively heat the water.
Yeah.
They just intelligently mix the hot industrial garbage with the cold ocean.
It completely eliminates the massive heating costs that bankrupt traditional inland aquaculture farms. By leveraging this thermal symbiosis, the Stolt Sea Farm currently produces roughly 400 tons of premium warm-water Senegalese sole every single year in the freezing subarctic, entirely sustained by the sweat radiating off a turbine next door.
That is mind-blowing thermal alchemy. But they aren't the only ones utilizing this specific heat cascade for heavy industry, are they? The source texts also detail companies producing high-end gourmet salt.
Yes, artisanal operations like Nordur Salt and Saltwerk. The traditional global method for producing high-quality crystallized sea salt usually requires one of two things.
What are they?
Either you need a hot, incredibly dry, arid climate to facilitate slow solar evaporation in massive outdoor shallow pools, think of the salt flats in the Mediterranean, or if you are in a cold climate, you have to burn massive, expensive amounts of fossil fuels to physically boil the seawater in vats until the water evaporates and leaves the salt behind.
Iceland obviously lacks the arid sun.
And burning imported oil to make salt is economically unviable. Instead, a company like Nordur Salt utilizes geothermal water piped in at just over 100 degrees Celsius to continuously boil the raw seawater.
I have a basic physics question here. If the geothermal water is arriving at exactly 100 degrees Celsius and standard seawater also boils at roughly 100 degrees Celsius, how does that work? How can 100-degree water effectively and rapidly boil another liquid that requires 100 degrees to boil? There's no temperature differential to drive a rapid phase change.
You are hitting on the fundamental thermodynamic hurdle they faced. If they just put a pot of seawater on a 100-degree radiator, it would take weeks to evaporate. So they manipulate the physics of the environment.
How so?
They pump the raw seawater into massive sealed steel chambers. Then, they use mechanical pumps to forcefully suck the air out of the chamber, creating a powerful subatmospheric pressure environment, a strong vacuum.
Oh, of course. Lowering the atmospheric pressure drastically lowers the temperature required for a liquid to boil.
Exactly. It's the same reason water boils at a lower temperature at the top of Mount Everest. Inside these specialized vacuum chambers, the atmospheric pressure is lowered so significantly that the raw seawater violently boils at just 51 degrees Celsius.
Which means the 100-degree heat is more than enough.
Consequently, the 100-degree geothermal water circulating through the heating jackets provides an overwhelming abundance of thermal energy. It rapidly, violently evaporates the seawater, triggering the crystallization of incredibly pure, perfectly formed gourmet salt flakes. It is a masterclass in combining applied thermodynamics with the cascade principle.
Okay, so the cascade gives us tropical fish and vacuum-boiled gourmet salt. But let's look at another traditional Icelandic staple, fish drying. I have to imagine that dehydrating thousands of tons of fish requires an absolute mountain of hot air.
A truly tremendous, almost incomprehensible amount of thermal energy is required to evaporate the moisture out of biological tissue on an industrial scale. Historically, for centuries, Icelanders dried fish the hard way, by hanging them outside on massive wooden racks along the coast, leaving them entirely to the mercy of the freezing, highly unpredictable, salty ocean wind.
That sounds like it would take forever.
It took months, and the quality varied wildly based on the weather. Today, however, it has evolved into a massive, highly precise, heavily industrialized indoor operation. Let's look at a major processing company like Hostek. Their primary business model involves drying massive quantities of cod heads.
Cod heads.
Yeah, which are considered a waste product by the fillet industry, but are highly prized and exported primarily to nations like Nigeria, where they are a vital, protein-rich dietary staple used in traditional soups and stews.
Just how much sheer energy does an operation like that consume to dry thousands of tons of wet bone and tissue?
The metrics are staggering. The Hostek facility physically purchases and pipes in roughly 1.3 kilograms of raw geothermal steam every single second of the day from the nearby Reykjanes power plant. Furthermore, this isn't gentle steam. It arrives at a punishing 18 bar of pressure and a blistering temperature of 210 degrees Celsius.
1.3 kilos of superheated, highly pressurized steam every single second. How do they actually apply that to the fish without just cooking them into mush?
So they utilize a massive two-stage heat exchange process. They don't blast the steam directly onto the fish. First, they use that intense 210-degree steam to rapidly heat a massive closed-loop reservoir of fresh water up to a highly stable 70 degrees Celsius.
Okay, so they heat water first.
That 70-degree hot water is then pumped through a labyrinth of massive radiators. Giant industrial fans blow ambient air across these radiators, instantly heating the air. This massive volume of hot, dry air is then continuously blasted over the racks of fish stacked inside massive, cavernous batch dryers.
And the air just sucks the moisture out.
The hot air absorbs the moisture from the fish tissue, carrying it away. By utilizing this pure, relentless geothermal heat transfer, the Hostek facility is able to process a staggering 12,000 tons of heavy, wet, raw cod heads into 2,500 tons of lightweight, perfectly shelf-stable, export-ready dried product every single year.
So we have established that heavy industries, aquaculture, salt refinement, and massive dehydration plants and all thrive symbiotically on the captured waste heat. But I want to introduce a genuine point of friction here. I want to talk about a completely different kind of industrial waste, the absolute elephant in the room for any major industrial or energy generation process.
Gaseous emissions.
Yes, we are talking about carbon dioxide and greenhouse gases. Because the narrative around geothermal energy is usually that it is 100% perfectly clean and green. But the reality is, geothermal power plants aren't entirely emission-free, are they? Poking holes into the Earth's crust has atmospheric consequences.
It does, and it is a critical nuance that is often glossed over in the green energy transition. They are absolutely not emission-free. The deep geothermal fluid drawn from these subterranean reservoirs contains significant amounts of what we call non-condensable gases, which have been trapped in the magma and rock for millennia.
What happens when they hit the surface?
When the fluid reaches the surface and the pressure drops, these gases separate and are released. The primary emissions are carbon dioxide and the highly toxic sulfur-smelling hydrogen sulfide. Now, to be fair to the industry, the total volume of these greenhouse emissions is merely a fraction, often less than 5% of what a comparable coal or natural gas plant produces per megawatt.
But it's still pollution.
But at the scale of an entire national grid, they are still pumping significant, measurable volumes of greenhouse gases into the atmosphere. However, staying entirely true to the Icelandic engineering model we've discussed today, they refuse to view this bubbling CO2 simply as a toxic pollutant that must be vented and ignored.
They see it as a resource.
In the Cascade mindset, they view the CO2 as a stranded, highly valuable chemical raw material.
Enter a company called CarbFix. I've read a little bit about their operations in the science press over the last few years, and honestly, every time I read about their process, it sounds completely like science fiction.
It is not science fiction. It is arguably one of the most important, scalable, and genuinely verified climate mitigation technologies currently being developed anywhere on Earth right now. Cardfix, which operates its primary flagship facility adjacent to the massive Helishite geothermal power plant, has essentially figured out how to reliably, permanently turn a greenhouse gas into solid stone.
Okay, I need you to walk me through the exact chemical and physical mechanism of how you turn a floating invisible gas into a rock. How does CarbFix actually achieve this?
The physical process relies on mimicking the Earth's natural geological carbon cycle, but accelerating it by millions of years. First, they mechanically capture the exhaust stream of CO2 and hydrogen sulfide directly from the power plant's cooling towers before it can escape into the atmosphere.
And they compress it.
Instead of trying to compress this gas into highly pressurized, dangerous liquid tanks, which is the standard, highly flawed model for traditional carbon capture, they simply dissolve the raw gas into massive, continuous flows of water.
So they are essentially injecting the exhaust into water, creating a giant industrial-scale batch of toxic sparkling water.
That is the perfect analogy. They create a highly pressurized, highly acidic carbonated fluid. They then take this heavily carbonated water and forcefully inject it deep underground, pumping it right back down into the exact same deep, highly fractured Pleistocene basalt rock formations we discussed at the very beginning of the show.
And what actually happens when that acidic, carbonated sparkling water hits the deep basalt? Why doesn't it just eventually leak back up through the fissures and escape back into the atmosphere years later?
Because of a rapid, permanent chemical reaction known as mineralization. Basalt is an igneous rock that is naturally incredibly rich in highly reactive alkaline metals, specifically calcium, magnesium, and iron. When the highly acidic, CO2-rich carbonated water physically washes over the porous basalt deep underground, the acid begins to dissolve the rock, releasing those calcium and magnesium ions into the fluid.
Oh, I see where this is going.
These positively charged metal ions immediately chemically bond with the dissolved carbon dioxide molecules. This chemical bonding triggers a rapid precipitation. The CO2 physically transforms from dissolved gas into solid, stable carbonate minerals specifically. It forms bright white veins of calcite interwoven directly into the dark pores of the basalt rock.
It essentially crystallizes inside the rock.
Exactly. And the time scale is the true breakthrough. Geologists used to think this mineralization process would take thousands of years. The CarbFix data proves that over 95% of the injected CO2 turns into solid rock in under 2 years.
Under 2 years.
Once it is solid calcite, it is permanently locked away in the Earth's crust. It cannot leach, it cannot escape during an earthquake. It is chemically inert stone. Through this single process, the Helishite plant is literally filtering out over 30% of its total CO2 emissions and a massive 75% of its highly toxic hydrogen sulfide, and turning it permanently back into the Earth.
Turning exhaust gas into rocks. It's brilliant. But there's another company operating in the Icelandic ecosystem doing something even wilder with the captured CO2. It is a company called Carbon Recycling International, or CRI.
Yes. If CarbFix's mission is to safely bury the waste back into the earth, CRI's mission is to use that waste to physically drive your car down the highway. CRI operates a massive facility taking the CO2 emissions directly from the Svartsengi plant. Their process is an incredible feat of chemical synthesis.
How does it work?
First, they capture the CO2. Then, in a separate process, they take pure water and utilize the abundantly cheap, renewable Icelandic electricity to run massive electrolyzers. These machines use electrical currents to violently split the water molecules apart into their base elements: pure oxygen and pure hydrogen gas.
Okay, let me track the ingredients. You have a silo of captured CO2 exhaust from the power plant, and you have a newly manufactured silo of pure hydrogen gas from the electrolyzers. What happens next?
They feed both of these gases simultaneously into a massive, highly pressurized catalytic reactor. Inside this reactor, under specific heat and pressure profiles, the carbon and oxygen molecules from the CO2 chemically bond with the hydrogen molecules. The resulting synthesized chemical compound is methanol.
And since it's all from renewable sources.
Specifically because every single energy input in the process, the electricity, the hydrogen, the carbon, was sourced from renewable or recycled streams, they are producing what is classified as renewable green methanol.
And what is the actual commercial application for millions of gallons of green methanol?
It is a direct drop-in replacement for fossil fuels. Their facility produces roughly 4,000 tons of liquid green methanol every single year, utilizing about 5,500 tons of captured CO2 exhaust to do so. This methanol is an incredibly versatile, energy-dense liquid fuel.
Can you just put it in a normal car?
It can be blended directly into standard gasoline at the pump to cleanly fuel regular, unmodified internal combustion engine cars. It can be utilized as a foundational chemical feedstock for producing low-carbon biodiesel for the heavy trucking industry. They are literally taking the invisible greenhouse gas exhaust from a power plant and chemically transforming it into the liquid fuel that powers the ships and trucks delivering goods across the island.
I want to take a moment to summarize this vast, interconnected web of industrial symbiosis we've just mapped out. The power plant drills a hole and pulls up boiling brine. It uses that heat to spin a turbine and make electricity. It passes the leftover heat to dry thousands of tons of fish for export. It uses the secondary heat to warm 30,000 homes and melt the snow off the public sidewalks. The hot condenser water is mixed with the ocean to farm tropical Senegalese sole. The microscopic silica that threatens to clog the pipes is harvested to cure autoimmune skin conditions.
And then the emissions.
And the toxic greenhouse gas exhaust that bubbles out of the ground is captured, split, and literally transformed into solid rocks and liquid car fuel.
If we connect all these disparate dots to the macro-level picture, Iceland's massive corporate industries are quite literally, efficiently eating each other's exhaust streams. They have successfully engineered a highly lucrative, highly resilient industrial food web.
Which brings us to the final, and perhaps the most futuristic, awe-inspiring section of our deep dive today. We've talked extensively about using geothermal energy for its raw thermal heat, its high-pressure steam, and its localized biological applications. But our deepest academic sources point to a massive, rapidly emerging global frontier that isn't about heat at all. It is entirely fundamentally chemical.
This is the precise intersection where deep Earth geology meets the absolute cutting edge of the future global energy transition. If you follow the energy markets, everyone from massive venture capital firms to national governments is talking obsessively about hydrogen right now.
Hydrogen is the big buzzword.
Hydrogen gas is widely considered the ultimate holy grail of green, renewable fuel. It is incredibly energy-dense by weight, and when you burn it in an engine or run it through a fuel cell to generate electricity, the only byproduct that comes out of the tailpipe is pure, harmless water vapor. It is the perfect, clean fuel.
But the massive multi-trillion-dollar problem with hydrogen is the process of acquiring it, right? You can't just drill a well in Texas and pump up liquid hydrogen like you do with crude oil.
Exactly. We have historically viewed hydrogen not as an extractable resource, but purely as an energy carrier that must be forcefully manufactured. And the current manufacturing methods are deeply flawed.
Because they use fossil fuels.
The vast majority of the hydrogen used in the world today is what the industry calls gray hydrogen. It is manufactured by a chemical process called steam methane reforming or coal gasification. Both processes require burning massive amounts of fossil fuels to strip the hydrogen atoms away from carbon molecules, which inevitably releases colossal, staggering amounts of CO2 directly into the atmosphere, completely defeating the environmental purpose of using hydrogen in the first place.
It's a shell game. You're just moving the carbon pollution from the tailpipe of the car back to the smokestack of the factory.
Right. Now, the alternative is green hydrogen, like the process we just discussed with CRI. You make green hydrogen by splitting water using renewable electricity in an electrolyzer. It is perfectly clean. But the massive hurdle there is that electrolysis is incredibly, punitively energy intensive.
It's just too expensive.
It requires vast amounts of electricity, making the resulting hydrogen incredibly expensive and difficult to scale to the massive volumes required to replace global shipping or aviation fuels. But recently, a radical paradigm-shifting question has emerged in the geological community.
What's the question?
What if we didn't have to spend billions of dollars manufacturing hydrogen at all? What if we could just prospect for it, mine it, and pump it out of the ground exactly like we do with natural gas?
Natural hydrogen, often referred to in literature as white or gold hydrogen. Our core academic source paper focuses specifically on this exact geological phenomenon. The central thesis is that the Earth itself is acting as a massive planetary-scale electrolyzer, manufacturing pure hydrogen for us deep underground. How does the Earth actually do that?
The mechanism brings us right back to the very first geographical feature we discussed today, the mid-ocean ridges. Deep beneath the surface at the divergent boundaries where the massive tectonic plates are slowly ripping apart, freezing seawater cascades down through the deep fissures.
Down into the mantle.
As this water reaches the extreme depths of the newly formed, incredibly hot, iron-rich rocks of the Earth's upper mantle, the immense heat and pressure trigger a massive, continuous chemical alteration of the rock. This specific diagenic process is called serpentinization.
Okay, serpentinization. That is a massive, intimidating word. I need you to break down the exact chemistry of this reaction for me. What is physically happening to the rock and the water?
It is, at its core, a beautiful, elegant, naturally occurring chemical equation. H2O plus 3 FeO yields Fe2O3 plus H2.
Okay, let's translate that equation to plain English for those of us who haven't taken a chemistry class in a decade.
Absolutely. You start with standard water molecules descending into the crust. This water eventually comes into direct physical contact with massive subterranean formations of ferrous minerals.
Ferrous meaning iron.
Ferrous simply means rocks that are incredibly rich in unoxidized iron, specifically a green rock called olivine. The environment down there is under extreme pressure and extreme heat, often exceeding 300 degrees Celsius. In this volatile environment, the water chemically attacks the iron in the rock. The water aggressively oxidizes the iron.
So it's rusting.
The oxygen atom is physically ripped away from the water molecule and permanently bonds with the iron in the rock, creating a new mineral compound called magnetite. This is essentially deep earth rust. But the critical question is, what happens to the two hydrogen atoms that were just violently stripped of their oxygen partner?
They have nowhere to go.
They have nowhere to bond in the rock. They are liberated. They are released into the subterranean fluid as free, unattached dihydrogen gas.
The water causes the deep mantle rocks to rust. And in the process of rusting, the rocks essentially exhale massive volumes of pure combustible hydrogen fuel. That is staggering.
It is the Earth's natural fuel factory. Now, since the deep-sea explorations of the 1980s, marine geologists have known that these natural hydrogen vents exist. They found them bubbling along the mid-ocean ridges deep underwater.
But they were too deep to reach.
Because they were located at the bottom of the Atlantic Ocean under thousands of feet of crushing water pressure and hundreds of miles from the nearest shore, it was considered economically and technologically impossible to ever capture or harvest that gas. It was a geological curiosity, nothing more.
But the light bulb just went off. Iceland is the only place on the planet where the mid-Atlantic ridge physically sticks up out of the ocean and onto dry land.
Precisely. Iceland is the terrestrial anomaly. It is the only place where we can directly study, access, and potentially drill into this specific oceanic extensional tectonic context without needing a deep-sea submarine. The thousands of deep geothermal boreholes drilled all across Iceland to harvest hot water provide scientists with a direct, unprecedented window into this deep Earth chemistry.
And when researchers finally began specifically analyzing the gas mixtures bubbling up through these terrestrial wells, the data they recovered was absolutely staggering.
It really was.
Give me the hard numbers from the academic reports. How much natural hydrogen are we actually talking about venting out of these wells? Is it just trace amounts, or is it a significant volume?
The researchers conducted a comprehensive analysis of the dissolved gas mixtures coming out of various high-temperature geothermal wells scattered across the entire island. They discovered a very specific pattern. The hydrogen concentrations are astronomically high, but they are highly localized.
Meaning what?
They only spike within the active neovolcanic zone, the exact narrow corridor where the tectonic plates are actively splitting apart. If you test a well outside that specific active zone, the hydrogen concentration drops to almost nothing.
So the hydrogen generation is entirely dependent on the active, ongoing tectonic tearing. Where were the biggest, most significant spikes recorded?
At a highly active geological site called Landmannalaugar, the researchers measured dissolved hydrogen concentrations reaching an astonishing 198 millimoles of H2 per kilogram of geothermal fluid.
Is that a lot?
Now, to put that abstract number into a scientific perspective, a millimole is a massive quantity of molecules. Finding 198 millimoles crammed into a single kilogram of water represents a phenomenally dense concentration of dissolved gas. It is roughly 7 times higher than the highest concentrations ever observed at the famous Ashadzi hydrothermal vents located deep under the Atlantic Ocean.
And what about the other site mentioned in the sources?
Moving farther north, in the highly volatile Namafjall area, the results were even more dramatic. The total non-condensable gas mixture aggressively venting out of the ground in that region was composed of up to a staggering 57% pure hydrogen by volume.
57% of the total gas volume. That isn't a trace element. That is a massive, highly concentrated, highly volatile stream of pure, zero-emission fuel just naturally venting out of the dirt into the atmosphere. Why is the Icelandic geology producing so much of it compared to anywhere else?
The researchers identified 2 highly specific geological catalysts that are actively supercharging this rust reaction underneath Iceland. First, as we discussed at the beginning, they have the highly fractured subglacial Pleistocene crust.
The sponge-like rock.
This incredibly shattered rock acts as a massive superhighway, providing a rapid, deeply penetrating, constant supply of cold meteoric surface water directly down to the deep, iron-rich mantle rocks, keeping the oxidation reaction constantly and aggressively fed with fresh oxygen. Second, they discovered a critical chemical nuance regarding the water itself.
What's the nuance?
The data showed that the highest hydrogen concentrations were deeply correlated with hydrothermal fluids that possessed very low concentrations of sodium chloride, or basic salt.
So salt actually inhibits the hydrogen reaction.
It does. Highly saline seawater slows the supendenization process down, but because Iceland sits above the ocean, it has massive glaciers and heavy rainfall. Therefore, the fluid penetrating the deep fractures is fresh, unsalted meteoric water.
Oh, that makes sense.
So, fresh glacial water reacting aggressively with fractured, newly formed iron-rich basalts at extreme subterranean temperatures creates the ultimate optimized natural hydrogen factory.
Okay, I have to step in and push back on the hype here. It is one thing to identify a massive, bubbling pocket of highly combustible hydrogen gas sitting underneath an active volcano. It is an entirely different, highly terrifying engineering challenge to actually drill into it, capture it safely, and pipe it out without causing a massive exclusion or destabilizing the fault line. Can we actually tap this safely on a commercial scale? And more importantly, is this just a localized Icelandic party trick, or does this have real implications for the global energy grid?
Your skepticism regarding the extraction engineering is completely warranted. Tapping a highly pressurized, highly combustible gas in an active seismic zone requires unprecedented engineering safety protocols, and the technology to capture it at scale without contamination is still in its infancy.
But the global implications.
To answer your second question regarding the global implications, the data from Iceland is completely opening up an entirely new paradigm in global energy exploration. Right now, the world's governments and massive energy corporations are spending hundreds of billions of dollars trying to figure out how to manufacture hydrogen cheaply in massive factories.
And we might not have to.
The data emerging from Iceland suggests we have been looking at the problem backward. We should be pivoting those billions into mapping where the Earth is already manufacturing it for free. If geologists can successfully map the specific subterranean conditions that favor rapid serpentinization, not just in Iceland, but in similar ancient geological contexts buried on shore around the entire world, perhaps in places like Australia, the United States, or parts of Africa, we could completely transition the global economy.
It would change everything.
We could move from the incredibly expensive process of manufacturing hydrogen to simply extracting it like natural gas. It has the potential to become the primary, limitless, absolute zero-emission baseload fuel of the future.
And once again, this tiny, isolated island sitting on a tearing fault line is serving as the primary living laboratory for the entire planet.
It all fundamentally comes back to that initial psychological pivot we discussed at the start of the show. The willingness to plug directly into the danger rather than run away from it.
We have covered a truly staggering amount of technical, historical, and geological ground today. For you, the listener, I want to take a moment to synthesize the massive journey we've just been on together. We started miles below the surface of the Earth, visualizing the slow, violent tearing of massive tectonic plates. We followed superheated, highly pressurized brine, rushing up through miles of subglacial cracked basalt to spin heavy turbines and generate baseload electricity.
And we tracked the waste heat.
We tracked the massive volume of waste heat from those turbines as it was captured and piped 27 kilometers to warm 30,000 residential homes. We watched the spent, lukewarm water from those living room radiators flow out into the streets to passively melt the snow off the sidewalks of Reykjavik, saving millions of dollars in infrastructure damage.
We even talked about bananas.
We traveled backward in time to examine the thermodynamics of subarctic banana plantations and forward in time to marvel at outdoor tomatoes wrapping their roots around heated pipes and delicate winter pansies blooming aggressively in the freezing Manhattan snow. We witnessed a masterclass in industrial symbiosis, where the thermal exhaust from one plant fueled the farming of tropical sole, the vacuum boiling of gourmet salt, and the massive dehydration of thousands of tons of codheads.
It's all connected.
We watched invisible toxic carbon emissions be dissolved into water and permanently turned back into solid stone, or split apart and synthesized into liquid fuel to drive cargo ships. And we ended our journey staring at the deep earth itself, realizing that the rocks beneath our feet are quietly breathing out massive volumes of pure, zero-emission hydrogen gas.
The primary overarching takeaway from this massive stack of technical sources is the necessity of a profound, radical shift in our macroeconomic and industrial perspective. In the Icelandic engineering mindset, a problem, whether that problem manifests as an apocalyptic magma plume threatening a town, a catastrophic chemical scaling of silica ruining expensive steel pipes, or thousands of tons of waste steam billowing out of a turbine, is never simply accepted as a permanent problem.
It is viewed strictly as an unmonetized solution waiting for the correct market application.
It is a radical, almost aggressive reframing of reality.
And the challenge I would pose to you, the listener, based on this deep dive, is to take this rigorous Icelandic lens and apply it strictly to the macro structures of your own world. Look closely at our urban planning, our global manufacturing supply chains, and our massive infrastructure projects. Where are the massive thermal leaks? What is the physical industrial exhaust, whether it is billions of gallons of wastewater, massive plumes of low-grade thermal heat, or mountains of discarded raw materials that our society is currently venting mindlessly into the atmosphere or burying in the ground?
Exactly. Could that very specific exhaust, that exact waste stream, be captured and utilized as the primary foundational fuel for an entirely new, highly lucrative industrial ecosystem?
That is the absolute perfect question to leave on. Because if a relatively small, geographically isolated island nation of just 380,000 people can successfully profitably engineer a complex ecosystem where the toxic CO2 exhaust of a power plant feeds algae for high-end skincare and the waste condenser water grows tropical fish in the middle of the snow. Wait, what actually happens when we apply this rigorous ecosystem thinking to the global industrial grid? Are we rapidly entering a technological age where the very concept of waste simply ceases to exist in the dictionary? It really forces you to look at that terrifying 15-kilometer river of magma slowly creeping under Grindvik in a completely new light. It isn't just an apocalyptic threat to be feared, it's the roaring engine of tomorrow.